Hello, everyone. I'm Zhangyu, a fourth-year PhD student from Huazhi University of Science and Technology. Today, I'm glad to present our recent work about lock-free index design for persistent memory, which is based on a paper published in UCNIX ATC 2020. In this work, we propose a clevel hashi, a quasi-consistent and lock-free hashi scheme for persistent memory to provide scalable query services for persistent memory. Due to the silent features of non-volatility, large capacity, better addressability, and DRAM-scale latency, persistent memory is promising to improve the storage system performance. In 2019, Intel released the first commercial product of PM, namely Intel Optane DC persistent memory, or Optane PM in this talk, which provides an attractive capacity of 512 GB per module. More importantly, the durability of PM enables instant recovery from data in memory. There are two operational modes for PM, memory mode and APP directory mode. In the memory mode, Optane PM is deployed as a volatile memory layer like DRAM. Hence, we obtain large memory without changing existing applications. In APP direct mode, we leverage the durability of PM and configure PM as a persistent memory layer, independent of conventional DRAM. As a result, it is possible to load data stored in PM to enable fast recovery, which, however, requires careful persistent memory programming. In the context of this talk, we focus on APP direct mode to fully exploit the non-volatile memory feature of persistent memory. Despite the silent features, PM also has limitations. First, due to the limited endurance and high latency to media, PM has high write overheads. According to recent studies, the low bandwidth of PM also constrains the concurrent writes. Second, the non-volatility of PM exposes data to inconsistency. For data larger than 8 bytes, they cannot be atomically updated by one atomic instruction. If the partially updated data are emitted to PM and the system failure occurs, the data in PM are inconsistent and corrupted. To address the partial update, a straightforward way is copying-based copy-on-write or logging. Specifically, copy the data to be modified and persist copy in PM. The partially updated data after crash can be recovered from the persist copy in PM. However, the cost is 2 times write overhead. Moreover, the persist order may be different from the issue order of store instructions. For example, the program allocates a new item before inserting the pointer to a slot. However, due to the cache replacement, the modified slot is persisted before the item, thus leading to an invalid pointer and inconsistency once failure occurs. To address the reordering, memory reference is required after persisting the new item. In summary, to mitigate the two limitations, PM applications should be write efficient to address the overheads and enforce the crash consistency for instant recovery. PM index structures are important for storage systems to provide fast queries. To support range query, tree-based indexes are group hierarchy layers with pointers, thus leading to high latency for pointer queries due to the pointer chasing. Unlike tree-based schemes, hashing-based index structures map items to flat space. The time complexity for point query is big O or 1. Therefore, hash structures are widely used in memory. For example, Redis and memcached. However, different keys may be mapped to the same location, called hash clearance. Typical solutions include linear probing and chaining with linked lists. However, when hash clearance cannot be addressed or the hash load factor cannot approach a threshold, the hash table needs to be resized to increase the capacity. The traditional resizing allocates a new table with 2 times as many buckets as the old table and rehash items from the old table to the new one, thus leading to high latency. Concurrency is important for PM indexes to provide fast indexing for terabyte scale PM data. Moreover, current Optane PM is equipped in data centers, which provide a multi-core environment for concurrent computing. In terms of PM hashing, leveraging the hardware parallelism to provide high concurrency is desired. Specifically, multi-reader and multi-writer concurrency with concurrent resizing enables scalable query performance. Recent schemes build PM hashing structures from existing concurrent DRAM indexes. CCEH is a crash-consistent extendable hashing. More than 1,000 slots shared one segment redirect log for queries. The dynamic resizing in CCEH requires a segment log and the potential global directory log, blocking concurrent access from other threads to items in related slots. Hence, the coarse-grained logs in CCEH limit the concurrency. PCLHT is a crash-consistent variant of cache-line hash table for PM. In terms of concurrency, PCLHT supports log-free search and the rest require bucket-grained logs. Though with one helper thread, the full table resizing for large table with global logs is still time-consuming, which blocks the insertion in other threads. Level hashing is a PM-friendly hashing index. It has 2 levels, and each level is an array of 4 slot buckets. When the 2 candidate buckets from 2 hash functions have no empty slots, level hash tries to move a stored item to its alternative candidate bucket in the same level with one-step movement, thus enforcing the write efficiency. The crash consistency is guaranteed by automatically updating the tokens in a bucket. Level hash rehashes 1/3 buckets for one resizing. Specifically, only items in the bottom level buckets are rehashed to the new level. Despite the optimizations for PM, level hashing has limited concurrency due to the inefficient logs. For interleaved search and insertion, the slot grained logs does not stop the concurrent data movement, thus missing inserted items for search operation. Moreover, original level hash leverages single-thread resizing, which blocks queries in other threads. In summary, for existing PM hashing index, concurrency is a bottleneck. To build a high-performance concurrent hashing index for PM, there are 2 challenges. First, the coarse-grained logs for shared metadata during resizing lead to performance degradation. Second, the locks in queries prevent concurrent access to the table. Moreover, the cache-line flushes and the memory fences in the critical path exacerbate the contention. Our work aims to offer a PM-friendly and high concurrency hashing scheme for persistent memory. In order to achieve this goal, we propose clevel hashing, a write-efficient and lock-free concurrent hashing scheme for PM. In clevel hashing, we design a multi-level structure without extra writes for insertion. Rehashing operations are performed in an asynchronous manner without blocking concurrent queries in other threads. For concurrency control, atomic primitives are leveraged to enable lock-free operations for all queries. There are three main components in our design, namely dynamic multi-level structure, non-blocking resizing, and lock-free concurrency control. Next, I'll introduce the dynamic multi-level structure. In real-world applications, the key value items are of variable sizes. To support variable length items, we store pointers in slots and actual items outside of the table via dynamic memory allocation. In order to achieve high load factor with low write overheads, clevel hashing takes three techniques to address hash clearance. First, leverage 8-slot buckets to provide multiple entries in one bucket. Since each slot stores a pointer to one key value item, an 8-slot bucket fits in the cache line size. Hence, one cache line access is required at most to search keys in a bucket. Second, use two independent hash functions to obtain two candidate buckets for a key in one level. Each level is an array of 8-slot buckets. 3. Manage levels dynamically. Specifically, levels are added for expansion and removed when rehashing in these levels completes. For two adjacent levels, the upper level has 2 times as many buckets as the lower one. Items share all levels but prefer upper levels. Note that, unlike level hashing, the techniques for hash clearance do not lead to extra writes for insertion when the table is not being resized. Hence, clevel hashing is write optimal for insertion. Let's begin the non-blocking resizing. In order to support concurrent resizing, we define level list and context in clevel hashing. A level list is a linked list to associate different levels. The context is a metadata structure with 2 pointers and a Boolean flag, including first level, last level, and is resizing. The first level and the last level are interpreted as the level with the most buckets and the least buckets respectively. The resizing in clevel hashing includes 5 steps. First, the thread to perform resizing makes a local copy of the globe context pointer. Second, dereference the local copy of context pointer and append a new level with twice the buckets of the original first level to the level list using compare and swap. If the compare and swap fails, update the local copy of the context pointer and continue with the next step, since other threads have successfully added a new level. Third, use copy on write plus compare and swap to update the global context by advancing the first level to new allocated level. When the compare and swap fails, check if the new first level's capacity is no smaller than desired, and the resizing is true. If so, update the local context pointer and continue, since other threads have updated the global context. Otherwise, retry the atomic update for global context. Note that the context size is only 17 bytes, containing 2 pointers and 1 Boolean flag, and the global context is modified only when resizing. Hence, the copy on write for context is lightweight. Fourth, rehash each item in the last level. The rehashing includes 2 steps. Copy the item's pointer to the first level via compare and swap, and delete the pointer in the last level. If the compare and swap fails, find another empty slot. If no empty slot is found, go to step 2 to expand the table. Fifth, when rehashing completes, update the last level in the global context atomically using compare, copy on write, and compare swap. For step 5, the failures of compare swap come from the modifications of global context in steps 3 and 5 of other threads. If the compare swap fails, try again if the last level in current context does not change. According to the operations in resizing, the 5 steps can be divided into 2 stages, expansion stage and the rehashing stage. The rehashing stage involves the migration of all items in the last level, which accounts for most of the resizing latency. In order to mitigate the performance degradation due to resizing, we leverage background threads called rehashing threads to execute the rehashing stage until there are 2 levels left. Hence, worker threads only execute the expansion stage so that the resizing no longer blocks concurrent queries in other threads. Note that keeping 2 levels of a load factor over 80% and limits the candidate buckets for 1 key to only 4, thus enabling high memory efficiency and low constant search latency for read-heavy workloads. Next, let's begin the lock-free concurrency control for clever hashing. The basic idea is to leverage the atomic visibility of pointers in slots to enable lock-free access. For lock-free search in clever hashing, there are 2 problems. First, frequent pointer dereferencing for key-value items lead to high latency. For pointer dereference overheads, we leverage summary tags to avoid unnecessary reads for 4 keys. A tag is the summary for a key. For example, the tag can be the leading 2 bytes of the hash value. To guarantee the consistency for the tag and pointer, we leverage the unused 16 highest bits of a pointer to store the tag. Hence, the tag and pointer can be updated by an 8-byte atomic write. The second problem is missing items due to the rehashing. As shown in this example, the matched pointer for thread 1 is moved by thread 2, thus leading to missing or inserted items for thread 1. To avoid missing items, we propose bottom-to-top search, that is, searching from the last level to the first level. When no item is found and the global context not changed, which indicate items may be rehashed to a new level, we redo the search. For lock-free insertion, we first conduct bottom-to-top search to determine if the key is already inserted into the table. Only if the key does not exist in the table, we perform the insertion. The consistency is guaranteed by persisting the new item before compare and swap the pointer. However, there are two correctness problems for the basic workflow. First, concurrent insertions of the same key into different locations may lead to duplicated items. Since both items are allowed for read, we propose to fix duplication in future update and deletion. Second, it is possible to lose new items inserted to the last level being rehashed. For example, thread 1 inserts an item in the rehashed buckets in the last level, and thread 2 reclaims the last level. As a result, the item inserted by thread 1 to the last level is lost. In order to fix the loss of new items, we design a context-aware insertion scheme to guarantee the correctness. Specifically, before insertion, check the context and not insert new items into the last level being rehashed. After insertion, if the table starts resizing and the item has been already inserted into the last level, we redo the insertion using the same pointer. For lock-free update, the pointers are updated automatically via compare and swap. However, duplicated items may lead to inconsistency after being updated. There are three cases for duplicated items: concurrent insertions with the same key, retry or context-aware insertion, and data movement for rehashing. We further classified the three cases into two classes according to the pointers. The first class is concurrent insertions. Two pointers refer to different items. In this case, keeping any one of the two is acceptable. The second class is two pointers refer to the same item. Since rehashing threads may delete the pointer in the last level, we keep the pointer which is closer to the first level. If two pointers are in the same level, keeping either pointer is identical. With this observation, we propose content-conscious find to fix duplicated items. Specifically, find the two pointers to duplicated items via bottom-to-top search. If two pointers refer to the same location, indicating the duplication due to the retry or context-aware insertion or data movement for rehashing, we delete the first pointer matching the key in the search. Otherwise, delete the first pointer with the item, since we only keep one item for concurrent insertions and with the same key. After the find, we get at most one item matching the key for update. However, even with content-conscious find, the interleaved update and rehashing may lead to update failures. As shown in this example, thread 1 first finds the item to be updated. Thread 2 copies the pointer to the item to the first level for rehashing. After thread 1 updates the pointer to the updated item, the contents in the slots are deleted by thread 2, thus leading to update failures for thread 1. To avoid update failures, a baseline scheme is to run find to check if item has been updated, which however leads to high latency. Clevel hash optimizes the update by filtering unnecessary second run find, since it is rare to simultaneously satisfy all the three conditions. The overall update overheads are acceptable. The lock-free deletion is also based on compare and swap. For duplicated items, unlike update, delete all unmatched items in the bottom-to-top search The lock-free deletion also has failures like the update. Hence, we leverage similar optimizations to avoid frequent execution of deletion. For crash consistency of log-free indexes, we follow the methodology of recent studies. Due to the atomic visibility of log-free hashing, it is possible to enforce the consistency by persisting the modifications with low overheads. Specifically, persist after PM writes and persist dependent metadata after loading them. In this way, we enforce the PM modifications are persisted and based on persistent data. Rehashing suites record bucket position for NPM after rehashing the items in the bucket. For recovery, rehashing suites resume from the last recorded bucket to continue rehashing. The possible duplicate items are handled in future update or deletion. We have implemented our clevel hashing based on PMDK with C++ bindings, that is, LBPM or BJCPP. In performance evaluation, we run our experiments using Intel Optane DC PMM configured in APP direct mode. The concurrent execution involves 36 threads in one NUMA node to avoid the disturbance of non-uniform memory latencies due to non-NUMA architectures. In the evaluation, we compare state-of-the-art indexes from both academical and the industrial community. For fair comparison, we ported clevel hashing, CCH, PCHT, and our clevel hashing to the same platform of CMAP, that is, Intel PMKV. For workloads, we use YCSB to generate macro benchmarks in zip-file distributions and obtain real workloads from YCSB as macro workloads. For load factor, the maximal load factor of clevel hashing is compatible with the original level hashing, that is 86%. Compared with level hashing, clevel hashing does not move items in the same level, which decreases the load factor. However, clevel hashing increases the number of slots to 8, which enables high memory efficiency. For macro benchmarks, due to the log-free search and summary tags, clevel hashing achieves lower average search latency than other schemes. The average insertion latency is affected by resizing. With correctness guarantee, the log-free concurrency control still enables low average latency for clevel hashing. For real YCSB workloads with different read-write ratios, clevel hashing obtains up to 4.2 times speedup than PCHT due to the log-free concurrency control and the non-blocking resizing. The throughput of our implementations may be lower than related work. The reason is that the performance overheads of C++ bindings of PMDK. We leave the evaluation of clevel hashing on top C-based PMDK as our future work. In conclusion, existing PM hashing indexes have limited consideration for concurrency. We propose a PM-friendly and high concurrency hashing index. The dynamic multi-level structure avoids extra writes for insertion. The crash consistency is guaranteed by enabling log-free index to be persistent with small overheads. Clevel hashing achieves high concurrency by non-blocking resizing and log-free concurrency control with correctness guarantee. Our results using real PM demonstrate up to 4.2 times speed up. We have released our open source code for public use. That's all. Thank you for watching.